Hey guys, welcome back. This is Unit 3.1, Ecosystem Stability and Change. We're going to start off with Part 1 notes, which looks at population density and dispersion. So what do you say we go ahead and get started with this? All right, let's go. So first thing we have to do is discuss the different characteristics of populations. Now, there are three main characteristics of a population that we are going to talk about in this section. The first one is geographic distribution. So in other words, what is the area inhabited by that population? What is their territory, their hunting ground? What is considered their home area? Then we have density, which is the number of individuals per unit area. So how many individuals are there of that population in that given area? Then we have growth rates, which is looking at the increase and decrease of the population. So how much does it increase or decrease by each year or each time frame? So that's just some of the things we're going to be talking about. I at least wanted to describe those in the beginning, and then we're actually going to talk about them in more detail coming up. So let's talk first about population density. So as we said, this is the number of individuals living in a defined space. So in other words, how many individuals are there in that population within their geographic distribution, within their territory? And we find this out by dividing the number of individuals by the size of the area. So the nice thing about this is it helps us to figure out and determine the health of a population. If the population is really big for that area, then that tells us that there are likely to be a lot of resources which allow the population to get bigger. However, can that area sustain such a large population, or can it lead to a population crash? Now, when I mean that we divide it, here's the formula down below. So population density equals the number of individuals divided by the area. So for instance, we can talk about there are 20 wolves in a 5 square mile area. So 20 wolves divided by an area of 5 miles squared gives us a density of 4 wolves per mile squared. This picture also kind of demonstrates it. Now each circle represents the same amount of area. So it's looking at the same area, but we're looking at it in 100-year increments. So here we have 1650, here we have 1750, and here we have 1850. Now each stick person represents 100 million people. So in 1650, there were 1, 2, 3, 4, 5 times 100 million, so 500 million people. In 1750, there's 1, 2, 3, 4, 5, 6, 7, 700 million people. In 1850, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 1,200 million people, or 1,200 million people, 1.2 billion. Now, which picture, even without knowing those numbers, just looking at the stick figures, which circle has the most stick figures in it? Well, the one in 1850. There's clearly more people here than in the other two circles. Now, even though the circles are the same size, in this year, in 1850, the population density of people was a lot greater, and that's just simply what we're discussing at this point. Let's talk a little bit about population dispersion. So this is looking at how the individuals of that population are spread out within a territory. There are three types. There's clumped, which we see here, uniform, and random. I'm going to talk a little bit about each one. I'm going to show you the picture, give you some examples. And we'll start off talking about clump dispersion. Now, in a clump dispersion, resources are spread out unevenly within the area. So what we tend to see is that individuals of the population are going to group wherever the resources are located. Now, not only does it help them get access to resources, but it also provides protection against predators, because a lot of times, like with the school of fish, as you see here, in the school of fish, sometimes when they're all, super close together, they can actually look like a larger fish, and that can fool some predators into thinking it's bigger than them, so the predator will leave them alone. And since you're always hanging out with your population, it also makes finding a mate a heck of a lot easier. Uniform is when you have individuals of the same species that are competing for resources, but the resources and actually the territory are very, very limited. An example of this would be penguins, and here we have a picture of the emperor penguins. So they do live on land or on solid ground, mostly. They live on ice or solid ground, and they usually live in a smaller area. Now, their food source is in the ocean. But what they're showing right here in this picture, notice how they're kind of evenly spread out around that area. And that's what we mean by uniform. They're just kind of trying to find their own spot of land, their own piece of the territory in order to claim as their own. And the last one would be random dispersion. So in this case, the resources are more evenly distributed within an ecosystem. Since the resources are more evenly distributed, it means there's less competition, and that can lead to these smaller groups within the same species. Now, because this is talking about resources being evenly distributed, this is least common of the three methods. However, we can see this one in plants more so. What I mean by that, like with the trees there, even though in a forest it looks like the trees might be evenly spaced, they're actually not. You'll have areas where the trees are closer together, areas where they're further apart. There might be a small clearing within the forest. And that's because of how the seeds disperse and where they grow. Now, if we're looking at the forest, and that means that there's going to be certain things that are going to be consistent. The temperature is going to be consistent. The amount of water will be consistent. The soil is more likely to be consistent. So the biggest feature is going to be wherever the seed lands, can it get enough sunlight? So that's why a lot of times plants have ways to disperse the seeds away from the parent plant. This way they're not competing with the parent plant in order to get enough resources like sunlight. So what you end up having is this random spread of seeds that land and start growing. And that's what we see with this random dispersion. Let's talk a little bit about population growth. So there are 4 factors that affect population growth. We have the number of births, so the number of individuals who are born into the population. We have the number of deaths, the number of individuals who die within the population, and the number of individuals that enter or leave the population. So in other words, the number of individuals who immigrate into the population. So they were originally part of a different population of the same species, but then they entered this territory and became part of this population. And the number of individuals who emigrate from that population. So they didn't die, but they decide to move on to a new area, a new territory. Let's go ahead and see how this goes. So we can look at this in terms of a mathematical equation, and it looks at the rate that the population is changing in size. So what is the growth rate of the population? Now at the picture below, kind of summarizes what we just said about the factors. So this is the population within their area. Births increase the population, deaths decrease the population. Immigration will increase the population, emigration will decrease the population. So we take like factors together and group them. So the factors that increase the population are birth and immigration. So we're going to add those two together. The factors that decrease the population are death and emigration. So we're going to add those together. And then we're going to subtract those from each other. So R, which is the size or the growth rate of the population, equals birth and immigration together minus death and emigration together. Survivorship curves, what these are simplified diagrams that shows the number of surviving individuals over time from a set of given births. Now, in other words, what it means is for the births of that year in that population, how many individuals were born and how long did their lifespan last? And from that, we actually tend to see three different trends. So in terms of survivorship curves, we label them type 1, type 2, and type 3. Type 1 is when there is typically fewer offspring born, but most of them are going to live longer lives and live closer to the maximum lifespan of their population. Type 2 is when survivorship is roughly equal at all stages. So the likelihood of dying young is the same as the likelihood of dying old, as opposed to type 1, where it was less likely to die young and more likely to die old. And type 3 is many offspring are born, but only a few of them will survive. So you have a lot of offspring, but most die young and only a few will die old. So here's what we're talking about. This is the lifespan in years or percentage. So the longer it lives means, or the higher the percentage, the longer it lives. And then survivals on a log scale. Yeah. So type 1, we have a higher percent here, or sorry, higher individuals, meaning that most of them are surviving here. Remember, this is the number of survivals. So most of them survive, and then as it gets closer to the max lifespan, that's when we see the decrease in individuals occurring. As opposed to type 3, where you start off with a lot of individuals, but you see that sharp decrease right away, meaning a lot of them are dying early and only a few are living longer. And then here, this is type 2. It's roughly equal at every stage, which is why it has a nice straight line. So type 1, an example of that would be humans. Most people only have like 1 or 2 children at a time. And those 2 children have a very high chance of surviving childhood and living to adulthood. As opposed to, here we have a clam, and with the clam or the oyster, they will send out a lot of sperm and egg into the water column and have a lot of fertilizations occur. However, most of the larvae that do occur, that do get fertilized and start growing, most of those larvae are going to die. Only a few of them are going to survive and mature into the clam or the oyster. And then here, type 2, we have a squirrel. It could die young, but the chance of it dying young are pretty much the equal of it growing up and dying old. All right. Let's talk about the two growth types in terms of graphs. So they are exponential and logistic. With exponential growth, we see the individuals reproducing at a constant rate, not by a constant amount. We're not saying that they are adding to every time. We're saying that they're increasing by the same rate. So they might be doubling every time. That's not adding to, that's multiplying by 2 each time. Now this occurs when conditions are ideal and resources appear unlimited. And as you can see in the graph, you see this nice sharp curve upward. So over time, the population will increase in size very quickly. As opposed to logistic growth, where it starts off looking like exponential growth. However, we'll notice that there is a point of maximum population growth, and then it starts to slow down. So it starts off with exponential growth, hits a point, and then the growth rate will slow down. And then we'll actually notice that it's going to stabilize and kind of plateau off. Now, the reason why the growth slows is because resources become less available. So what once appeared like unlimited resources when you had a smaller population became limited resources for a larger population. As a result, the population growth slows down and the population will stabilize along what's called the carrying capacity. The carrying capacity is the largest number of individuals that a given environment can support. Now, typically what happens is it won't necessarily just go straight along that line. It'll kind of go up and down a little bit. Nice little like transverse waves up and down. All right, let's talk about some additional resources, shall we? All right. Bar. Oh well. So here we have 4 videos that I made with my Science and Pajama series. We have population growth rate and density. Oops, wrong one. Sorry. Which you can see there. And then we have population dispersion. Silly. Population dispersion. We look at the 3 different dispersion types: clump, uniform, and random. And then we have the survivorship curves. So we explored those 3. And then we have growth types. We'll talk about those as well. For other videos, we have Bozeman Science, population ecology. We have exponential and logistic growth in populations by Khan Academy. We have James Keenan, population ecology. We have Craig Savage, population ecology part 1. And Craig Savage, population ecology part 2. All right. So I hope that helps you guys. I hope this entire presentation kind of helped you to understand what's going on and all that good stuff. Definitely check out some of those additional resources for further explanation on these topics and contents. I will post the link for this Prezi in our video description so you have access to the additional resources. And yeah, other than that, if you have questions, hit me up in Google Classroom or email or in class. So you guys take care of yourself, stay awesome, stay curious, and most importantly, stay safe and healthy. All right, you guys, take care of yourselves. Bye-bye.